From this deep dive, all our team will present. Each person will give the talk for some of the components here. So I will start first. Each of us about 10 minutes. So we separate it into few short topics here. What? The part 1 is the multi-cluster physical setup. Then the part 2 is the Kubernetes, Helm, and the OMAC. Then we will describe the subscriber monitoring service. Then the monitoring and the virtualization by Doyoung. And the last one is the CDXOS in COMAC here. So I will go to the first one here. For the setup, we will show it start from tomorrow. We have a local cluster here. And then this cluster is inside the ONF Connect, this conference. We already shipped it here. And together with this cluster, we call it an edge cluster. And it together with the RU and the phone here. And in the remote side, we call it a central cloud. It's located in ONF office in Menlo Park. So it's across cities. And here we show the cross cities in this year MWC. We show the cross countries. We have the edge pod in the Barcelona, the MWC conference. And this side is in the GT side. So let's see the VOM for the multi-cluster. First is the edge cluster. This is the standard setup. If we want to build a code, then you can use the hardware here to quickly, just maybe 1 hour, to build your own COMAC platform. Here we normally standard need 3 x86 servers, and we suggest Haswell macro architecture or better. And each server should configure 2 interfaces, hardware interfaces. One is 1G, one another 10G interface. We use standard 4 OpenFlow switch for the fabric. And we tested the edge core, the Acton 6712, this model. And we also need a layer 2 switch for the management plan. And this one can be any type of switch here. Then we need the fiber cables. Here we use the breakout cables and 1 breakout cables and 6 the normal Ethernet Cat6 cables here. And for the central cloud, yeah, it's a little bit simpler. We also use 3 servers, the switch and the cables here. So the edge cloud cluster here is the standard setup. Okay. For the run and the end device, so far we tested the Samsung J5. The Android system is 7.1.1. And for the base stations, we tested the small base stations. The first is from the KVM standalone in Node B. This is the model number there. And the second run we tested is with the Acceleron here. And this is a splitted architecture. This is RU side. The control unit including 3 containers. We run the 3 containers on the Kubernetes cloud here, which include the NAT, Redis, and BBU. You can treat as the control unit of the Node B here. The model number is E1000. So let's take a look how to set up the one cluster. Let's take the edge cluster for example. First, we have 4 servers in the conference, and 3 are used as the Kubernetes. And the last one used for VPN to connect to our Menlo Park office. So based on this, we use the fabric, the OpenFlow switch, connect all the service. And then for acceleration, especially the mobile traffic, we will use the SRV for acceleration. The fabric connected to the SRV interface, which is 10G interface on server. The next one, we have one layer 2 management switch connected to all the 1G interface, which will run the Calico of the Kubernetes here. So here is the physical setup. Also, we on the run side together with the end device, we will have 2 phones here. And for the software layout, this is the edge cloud. So as I said, we want to move the data plan, the packet gateway. Here we use the S gateway and the packet gateway data plan combination as one SP gateway user plan. So if we move this gateway to the edge here, you can see the SPQU is at the edge at the conference here. And of course, for the management orchestrator, the XOS ONOS, together with the application control the fabric and the application control the run for the run slicing is also located in the edge here. And we also have the CDN. Later on, we will show an open source CDN solution integrated in the COMAC here. The CDN local also here. Here is the software layout for the edge cloud. And then it further go to our Menlo-Park office, the central cloud here. And let's quickly review over the central cloud here. We want to run the 3 GPP control plan, the MME, HSS, the database, even the SP gateway control plan here. We run the 3 GPP control plan all on the remote cluster. And for the run CU here, we also moved to the remote cluster. And yeah, this is the layout of the software in our remote central cluster. And let's see the next one, after the hardware and software layout, let's see how Fabric works in the COMAC. In OF, there is a project we call it Treeless. There is a wiki. You can see more detail about the how to looks on the network have problem again. Okay, I have some caches I think. Oh no. Okay, later on you can open it by yourself. We have the Treeless project wiki. It's a very detailed introduced in each version and like how from hardware, from cabling, from software, step by step, everything there. So you can follow the instructions there. So for the COMAC, we just use the Treeless project for the Fabric connectivity. So as COMAC team, we only introduce how to use it. So for the OpenFlow switch, we have one-time work after we get a brand new switch. And there are 3 steps. First, install the Linux, the operating system, and then install the OpenFlow driver, and then connect the management port to ONOS. That's all. This is the manual work. Then, if normally the OpenFlow switch is with 32 and 40 gigabytes the ports. So, but the server normally is 10 G interfaces. So here you may need a further modification. Need a further modification in this file to change the 40 gig interface to 10 G. This is all the manual work for the first time you need to do. Then for the Fabric, we need an application we call the segment routing. And of course, it also depends on other applications like the host provider, the OpenFlow, the other applications here. And for the configuration, here we also have examples like how to configure, because each use case or scenario, maybe you have your own topology, and you want to configure according your own topology, configure your network. So you can write down your own configurations. Here we have examples. And after write down your own configuration, you just use a command line pushing the YAML file to our XOS. Then everything is done. And after that, you will see in our UI, XOS UI, you will see the switch showed up here with some information like the drivers, like the ID, some detailed information here. Okay. For the configuration, my colleague will incur more detail here. In the general idea is we can treat the whole fabric, whether it's 4x4 or you only use one, we can treat the whole fabric just as a single router. When you configure router, you need to configure the subnet, the gateway. Similarly, here, if you want the fabric to route your between different subnet, you also configure it. Similarly with the traditional router. Okay, the next one is Kubernetes Ham and OMAC. Yeah. Why? We have both. This release, we released with OpenFlow. Uh, we have we have two versions. We have OpenFlow for the fabric. Also, you can use P4. Like in Barcelona, we should use P4. And also further, the P4 is not just for give the connectivity. We also implement the SP gateway U inside the P4 switch. We show the two features together. Yeah. So for this release, we just select one. If you want to use the P4 for connectivity and for the SP gateway U, we also open source. And people can use. You can choose it anyway. This is the more common here. Okay. Yeah. All the slides later on will be available. Where to download the slides? I think normally each year after the ONF Connect, we publish videos slides all online on the ONF Connect website online. Yeah. Okay.
Hi, I'm Hyunsun, and I will. COMAC is a system that runs on Kubernetes, so I will briefly introduce Kubernetes and Ham, and see how OMAC is implemented to be run on Kubernetes. Kubernetes is the most popular open source container orchestration system. And to run your application on Kubernetes, you just define your application as a Kubernetes resources. Like typically the process you're running your application become a pod or deployment, and configuration files becomes config map, and virtual IPs that proxies your multiple instances of applications becomes a service. Once you change your application to Kubernetes resources, then Kubernetes will take care of deployment and management and even scaling. Hamchart is a collection of files that describes related set of Kubernetes resources. Assume that your application is composed of one deployment, one config map, and one service. You may want to package them all together. This is the basic concept of Hamchart. And Hamchart can be stored locally or fetched from remote chart repository. One of the great things about using Hamchart is that you can reuse Hamchart that developed by others. Like we use Cassandra and ELK stack chart from official stable and incubator Hamchart repo. And you can also easily share your Hamchart to public. And actually, the Hamchart itself is not the final Kubernetes resource that you can directly apply to Kubernetes cluster. Ham is the one that creates actual Kubernetes resources that can be deployed on Kubernetes. And it is composed of Tiller, Hamchart server called Tiller, and client tool called Ham. So when you run Ham install your application, the request is sent to Tiller server, and Tiller fetches that required Hamchart from Ham repo, and it renders the Hamchart and requests are deployed to the Kubernetes cluster. And it also manages releases and revisions so that it can easily update it or even roll back to the older version. This is the Hamchart that we use to deploy our whole COMAC system. The core platform and COMAC platform is an umbrella Hamchart that includes multiple subcharts inside it. And there's a OMAC control plane Hamchart and OMAC data plane Hamchart. and CDN local and CDN remote as our example services. And besides this Hamchart, as I mentioned, some chart has a dependent chart from official Hamchart repositories like Cassandra for HSSDB and Prometheus, Grafana for monitoring, and ERK stack for logging. It actually takes about 20 minutes to install all these Hamchart to a Kubernetes clusters normally. And And you can find all these Hamchart from that URL. It was a quite short time to explain Kubernetes and Hamchart. I hope you get just an idea of what it is. And from now, I am going to explain how OMAC is implemented in COMAC. Actually, we have a deep dive session of OMAC later today, so I will focus on how it runs on Kubernetes. This diagram shows OMAC and its surrounding elements. OMAC itself is composed of database, HSS, MME, SPK, C, and U, and there are multiple control plane networks like S1AP, S11, S6A, and SX, and there are two data plane networks, S1U and SGI. And there are RAN-side elements here and fabric here, and ONOS SDN controller controls this fabric and RAN. This diagram shows example deployment of OMAC on Kubernetes. So each box here inside the node is a pod that running the named processes. And as I mentioned, this is an example deployment. So this pod can be scheduled differently. So MME can be deployed in node 1, and HSS can be deployed in node 3, and so on. And as you can see, all pod are attached to Calico networks, which is the main pod networks we use. And we use this main pod network for all control plane packet traffics. And Calico is called a CNI. CNI is a kind of network plugin in Kubernetes, and which is very popular and stable CNI that assigns 32-bit mask IP address to all pod and routes all traffics between pod. And as you can see, there are two in the node 3. There are two data plane components, SPK-U and CDN local. They have one or two more data plane network interfaces. Let's see more about data plane networks. Yeah. I'm sorry? Oh, CU. Is that it?
Is that just the control plane part, or that has both user and the control plane? Oh, just control plane.
Yeah.
So the user plane part of the CU is not in the picture?
Yeah. Yeah, you can see in this picture the RU part is
So you basically, the CU there is really the CUCP, not the CUUP, right? Okay, so you basically isolate the RC out into there. Okay.
Okay, let's see more details about data plane pod. So for data plane, we need additional two networks besides the main control plane networks, S1UNet and SGINet. We define these additional networks to Kubernetes with network attachment definitions. And typically Kubernetes pod comes with only one network interface. So we have to use a special CNI called Multus. Multus is a kind of meta plugin that allows calling multiple CNIs, multiple network plugins to Kubernetes pod. So the actual plugin we use for data plane is this one, VFIO VETH. You might never heard of this CNI because we use DPDK and SRIOV for our data plane for to get the best performance. So this VFIO CNI plugin is implemented by OMAC people for just for our FPGA U support. So basically, this CNI assigns. Basically, this VFIOV CNI assigns a virtual function to pod per interface, and attaches and creates more VET peer for this interface for pipe the control plane to corner. So with this CNI, we can create this multi-home pod. So you might want to wonder how Kubernetes scheduled this special SP Gateway U pod to a node that has enough VF resources. This is done by SRIOV plugin. This plugin runs on every node and it monitors the physical function that configured, and it reports to Kubernetes that how many SRIOV resources are available on this node. So this way, Kubernetes can schedule the SP Gateway pod to a proper node. So this is the last slide of my presentation. Let's see more details of how OMAC is implemented as a Kubernetes resources. First, let's assume that we have successful deployment of Cassandra cluster for HSSDB. And currently, all OMAC resources are implemented as a stateful set and does not support a multiple instance yet. And basically, each pod runs one or more containers inside it. This is MME pod. And this is SPGATC pod, and this is SPGATU pod. And all pods has dependency to other pods. So, for example, HESS has a dependency on Cassandra, and MME has dependency on HSS, and SPGATC has dependency on MME. And these dependencies are specified in pod spec. SPGATU also has dependency on SPGATC, but they can be deployed on a separate clusters like Edge and central. So we didn't specify that dependency to the pod spec. So admin have to be manually resolve that dependencies. And to make services talk to each other, we create a service cluster IP type services. And cluster IP can be only accessed by a pod that runs in the same cluster. So we also need a node port type of services. So that like node B, which is not included in the Kubernetes cluster, it's outside element, can be accessed. Or SPGA2C and SPGA2U, which is deployed in a separate cluster, can be talked to each other. And some applications like HSS and MME, they don't allow this VIP access with this kind of VIP. So they have to talk to each other with pod DNS or pod IP directly. And we have two jobs that creates initialized HSDB and creates initial user and MME data into the HSDB. And yes, this is all on my part. And next, my colleague Bedrina will present subscriber monitoring. Sure. Yeah, it's just a standard normal communication. We haven't implemented it. Yeah, not yet, but we have planned to do that kind of thing.
Yeah. Hello, everyone. Can you hear me? Yes. Hi, everyone. This is Badrinath here. I'm going to be presenting a topic on the subscriber monitoring feature that we are trying to introduce on the OMAC. Could you go to the slides? Yeah. Next page. So basic presentation today is for a subscriber monitoring tool, which we have started building an experimental version of it, and this we are planning to evolve into a better version. The most of the tools that you have for monitoring currently would monitor the pod status and the metrics on the pods and stuff. So in a use case where the operators would like to know about what kind of subscribers are present inside the system or the user level information on the QoS info or the tie level info. So this tool is basically required to query the components and get information from those like components like MME and the P gateway, or later directly from the like the database function, which will be there in part of the 5G. So as of now, the current implementation uses the IMSI to query the MME and get the information. But we plan to evolve it into maybe a token system where we don't have to expose this critical information of the user directly to fetch the information. The information that we would be able to receive from the context of the users from the various applications would include the QoS info, the tracking area info, the data flow information, or how many times the PCC rules change, and the TAID information. So basically all this information which will help the network operators make better decisions on configuring the network. Like they can get information, or they can use data analytics tools to understand how many users are working on which APN, or how many users are from a particular eNode B or on a particular tracking area. So all this information helps them make better decisions. Currently, the idea is to keep the query method to be REST-based APIs, and the information can be categorized as per the various authorization and different kind of logins. Like so, next page. Yeah. So as of now, we have a very basic experimental design what we have created to query the MME for the subscriber information. So currently what the tool will do, it will do the query to the MME. So basically we have a Python Flask server running as the HTTP server. This we have installed on the basic host machine where the MME is running on the container. And since the server, Python Flask server is running, so we can access the information using some URLs which we have defined for fetching the information. To enable this, we have to we introduced an IPC mechanism between the Python Flask server and MME app. So the MME would listen on a Unix domain socket, which is created on a shared folder between the host machine and the container. And the Python tool itself acts as the client and queries the MME whenever it receives any get or get API from the browser. Depending on the kind of URL, it will query the MME for that particular information. Currently, this is a basic, a very minimal approach of what we want to create, and we would like more contributions on this and try to evolve this more. So in the future, this could be fetching information from a data store directly, and it will be something like we can integrate it with a Prometheus and Grafana kind of tools where all the applications can write the data in a particular format which we want to like query about the subscriber, and then this can be accessed and the data can be given in a graphical method, and more data analytics tools can be run on that. So I would like to show you how the page is currently now. Maybe the next page. So basically, currently now we can see the first snapshot in which we can access the host IP and try to IMSI info is what we use as the URL. When we run this, basically it queries, it sends a REST API to the server or Flask server running. The Flask server queries the MME and fetches the IMSIs that are present from the user context inside the MME. So once the MMEs, once the IMSIs are fetched, we provide a hyperlink on the IMSI which creates another API to be queried towards the MME to fetch the rest of the information, including the the bearer ID, the MCC, MNC, and all kind of information like this. So once this information, this is a basic idea of how the tool works currently. This is a very minimal approach that we have currently, and we would like to evolve it as we proceed. Yep. So this is for the subscriber information tool that we wanted to present. Thank you.
The monitoring and visualizing part in COMAC environment. And it looks a little bit simple, but it's also important because we should know what's going on in our COMAC environment. And we are usually using Grafana and Prometheus for that. First, let me explain our general design for monitoring and visualization in our COMAC environment. COMAC should support two different network access. One of them is broadband network access, which is handled by Shiba project, and the other is mobile network access, which is handled by OMAC project. And they are deployed based on the code platform, and we don't want to use multiple monitoring services to monitor each network access, such as the Shiba part and the OMAC part. So Our COMAC platform designed to use only one monitoring service. It means that we only use one unified monitoring service. And the basic component of the unified monitoring system is the Kafka. So our COMAC platform actually consists of several components like this. One of them is XOS and Volta, ONOS, and so on. And they can post their own event metrics and logs into the Kafka. And basically, when we deploy code platform on our edge side, then it also deploys the logging system and monitoring system like this. And this logging system and monitoring system can interact or can deployed by code platform by default, and they can interact with Kafka to collect the information, such as logging information and the metric information to visualize something. So in this presentation, we are going to focus on the monitoring part, the bottom side. And monitoring part consists of three parts like this. First is the exporter and Prometheus and Grafana. Exporter is responsible for exporting metrics for Prometheus. And exporter collects some metrics from the Kafka data event burst and inserted the metrics to the Prometheus, which is the database to Prometheus. Then next step is to show this data to users. So Grafana can collect this, can use this data which is stored in the Prometheus database and create the dashboard and to provide this dashboard to users. So finally, users can check what's going on in our COMAC environment by using Grafana dashboard. Then let's talk about in more detail how to deploy this monitoring part based on the code platform. Actually, we can just use the name monitoring Hamchart to deploy our monitoring system. And for your understanding, name stands for Network Edge Mediator. And name monitoring consists of two subcharts like this. One of them is Grafana and the other is Prometheus. As I mentioned in the previous slide, the Grafana is just for creating dashboard for users, and the Prometheus is a database to collect metrics from exporter and store the metrics inside. And also, actually, when we try to install name monitoring based on our code platform, then name monitoring is also deploys two exporter. One of them is node exporter, and the other is a kubestate metrics. And node exporter is responsible for exporting node level information for users. And the other kubestate metrics exporter is responsible for exporting pod level information. So when we use the two exporter, we can get node level information and pod level information. It means that we can monitor each node on our cluster and also each container running on each our node. And actually, when we try to install code platform, this code platform try to deploy the name monitor Hamchart based on our platform. And actually, in our environment, we only install code platform on the edge side. So it means that name monitoring is also only deployed in the edge side. It means that we can monitor all nodes and paths deployed on the edge cluster. However, in our COMAC environment, we use a multi-cluster scenario. So we need to collect some data from the remote side. For name monitoring, default name monitoring does not care how to collect the data from the remote side. So we need to consider how to collect the data from central side. So I will show you how to do it in the next slide. This is our very simple topology in our environment to install COMAC platform. And we have two clusters like this. The left side is the central side and the right side is the edge cluster. So when we try to deploy code platform based on the edge side, then it installs the name monitoring Hamchart like this by default. Then name monitoring includes the Prometheus and Grafana. Then next step is that name monitoring tries to install node some kind of exporter based on each node like this. Then Prometheus intervally collect data through this exporter, and Prometheus can collect local data from in the edge side. Then Grafana can show the information by using this Prometheus, because now Prometheus collects the local data from the edge side. But in this step, we don't have method to collect the remote side information like this. So we need to collect the information from central side. So the easiest way to collect the remote side is to install exporter like this. So you don't need to install whole monitoring system in central side. You can just install the exporter in the central side. Then each central node has a exporter like as well. Then Prometheus can collect this information from the central side by using this exporting the exporter in central side like this. Then Prometheus can collect all of the data in our multi-cluster scenario. Then Grafana can show all of the information about the central side and edge side in this centralized manner. And then next question will be, okay, we know how to collect the data, then how to create a dashboard to show this data. And it can be a little bit difficult for beginners. So fortunately, we already provide the default dashboard in our name monitoring Hamchart. There are 7 default dashboards provided by name monitoring like this. So if you log into the Grafana dashboard, you can check that there are already 7 dashboards allocated here. So you can just click one by one to check what is the default dashboard provided by our name monitoring Hamchart. Then among them, let's show you the some of the dashboards to you. So one of the example is OMAC dashboard. As I mentioned before, we focusing on the multi-cluster scenario, and in the OMAC component, each OMAC component is distributed in central side and edge side because MME and control plane is deployed on the central side, and the data plane deployed in the edge side. But now our Prometheus can collect the data from each cluster side. So this dashboard can show all OMAC components just by using this dashboard. So it shows that how much CPU cores and memory are requested by each OMAC component, and then it is now current usage of CPU and memory as well. And also it shows the network traffic, inbound, ingress and egress traffic for each OMAC path. So by using this dashboard, we can check our OMAC components going well or not. And next example dashboard is the node exporter dashboard. This information exposed by the node exporter, which we already installed in each node. Then by using this dashboard, we can easily check our node job works well and how much overhead exists on each node by using this dashboard. So already we provide 7 dashboards like this, but you can expand your own dashboard, and also you can just refer this dashboard as a sample, so you can make your own dashboard. So if you want to make your new dashboard, you can also contribute your dashboard into this name model Hamchart. So this is the end of my presentation, and next part, Woojoong will explain CDN and XOS in COMAC in more detail. Okay.
Yeah, we use the ONAP before, and like the ONAP design, we use the REST slicing for the together with the ONAP, together with the Turkey token, and in our overall architecture here, the ONAP like a central orchestrator, central like the overall orchestrator there, and the what we discussed is for the mobile for the COMAC edge access network here. Yes, it's similar. Yes, if you use the the Grafana Prometheus, it's all similar here. Yes.
Actually, our code platform includes the as I mentioned before, our code platform includes the logging system and monitoring system. And the Prometheus and Grafana is including the monitoring system. But in our environment, we only install the code platform on the edge side. So this is why we only have Grafana and Prometheus in the edge side. So it depends on you. If you want to install code platform or net monitoring in the central side, you can also deploy it in this net monitoring part in the central side. Yes, by default, it included in the code platform. But if you don't want to deploy this net monitoring, then you can optionally disable this net monitoring. So it is up to you which point you want to deploy this monitoring system. But basically, it's default option in our code platform.
Finally, we extend about 10 minutes to finish the last session about the CDN here.
Hi, I'm Woojoong from Open Networking Foundation. This is the last part for this session, and I will cover about CDN and XOS in COMAC. First one is CDN. CDN stands for Content Delivery Networks, as you know. So here is our OTT applications in COMAC. So our here the left figure is our COMAC platform stack. So CDN, and it is running on the Kubernetes environment, and also to deploy the CDN, we are using Helm. So the purpose of the CDN is to support the video streaming in the multi-cluster environment, and of course, we developed the CDN with all open source software. And also, here is our basic design. So CDN has a CDN remote and CDN local. So we deploy CDN remote in the central cluster, and CDN local is running on the edge cluster. CDN remote has two containers. First one is anti-media server, which is open source media server. And the last one is FFmpeg container, which is video archive. And FFmpeg is, as you know, it is open source coding and decoding software. And the last one is Nginx, which is an open source web server, and we are using this server for our local CDN server. So here is our environment. So we have two clusters, as I mentioned before. So first one is edge cluster, and the last one is central cluster. And of course, they can communicate with each other through internet. So we deploy CDN local on edge cluster, and CDN remote is running on central cluster. CDN remote basically has multiple video files inside, and also CDN remote makes those files into several video streams and then manage them. And also those video streams, of course, will transmit outside. And then CDN local should pull video streams from a CDN remote. And of course, CDN local has some cached video files. And finally, CDN local streams both cached and remote videos to UE equipment. So we are developed our open source CDN to fit those requirements. So we have two scenarios. The first one is to play the remote video files. So here we have a video archive. Video archive, of course, has some video files, and this video archive transmits some videos to media server by using ITMP protocol. Then media server finally transmits outside this stream, also with ITMP protocol. Then CDN local, in the CDN local, CDN server pulls one or some of those streams from CDN remote, and then CDN starts streaming services, if UE can access to CDN server through EPC and LAN, then UE can play remote videos. That is the first scenario. And the second scenario is to play the cached video file. So
As I mentioned before, CDN server has several cached video files. And with that, CDN server starts streaming services. And finally, you can play cached videos. That is two scenarios in CDN. So we have now three components here. First one is CDN server, second one is media server, and the last one is video archive. So as aforementioned before, we are developing those CDN with all open source software. So for CDN server, we are using Nginx, which is an open source software, and we containerize it to run on Kubernetes. And the second one is FFmpeg container. So FFmpeg, as I said, is open source coding and decoding applications. And this one is video archive, so of course it has several video files. And for media server, we are using an Antimedia, which is an open source media server. So we have three containers, and for deployment on a Kubernetes environment, we make two Helm charts. First one is CDN local Helm chart, and the last one is CDN remote Helm chart. That is the end of CDN, and let's go to the XOS. XOS is our orchestration. Actually, in the video archive, we have basically three files. So it has same contents but different bit rate: 36p, 480p, and 720p. So it depends on you. For example, if you have a good performance, good network bandwidth and radio bandwidth, then you can play a 720p. It's up to you. You can configure it. But we support three types of configurations, and once you deploy the CDN remote, you can configure it. You can change the value. Oh, not yet. Yeah. We can manually write down the code. Any other questions in CDN? Let's go to the XOS part. It is our orchestration software. So here is the XOS. The purpose of the XOS is mainly an orchestration. So XOS defines some services which is running on the platform, and it monitors some Kubernetes paths and also configure fabric networks and radio access networks, when slicing part. So here is an XOS workflow. So for XOS workflow, we need four elements. First one is Tosca files. Second one is XOS core, and we need two ONOS controllers. First one is ONOS fabric to configure fabric network, and the last one is ONOS RAN to configure radio RAN slicing. To communicate between XOS and ONOS controllers, we need a synchronizer. So Tosca files has several definitions. So profile definition, fabric switch definition, and UE and RAN slicing definition inside. And XOS has XOS Tosca components which can process those Tosca files. And XOS has several servers as services running in COMAC and through some service chains, and also configuration UI XOS has. And then synchronizer has monitoring and configuration part. And monitoring means ONOS monitoring, ONOS container monitoring, and configuration. And then first, ONOS Fabric has fabric monitoring applications and configuration application, and ONOS RAN has RAN monitoring and RAN configuration applications. So the first workflow is to add a COMAC profile. So in the profile Tosca file, we need to define ONOS application, which is running on COMAC platform, and service definitions, and we need to write down the dependencies. And then we send those files to XOS Tosca, and XOS will make some services, and then through service chains according to the dependencies. And XOS service make configuration UI. And then also, as I said, synchronizer is to communicate between XOS and ONOS controller. So we need to make synchronizer for each ONOS controller. So we make, XOS make two synchronizers. First one is for ONOS Fabric, and second one is for ONOS LAN. And then synchronizer starts to monitor that is profile workflow. And then the second flow is to install the Fabric configuration. So in Fabric file, we need to define node configuration, which we will use, and the Fabric switch configuration and port configuration. Of course, we send these files to XOS Tosca, and XOS Tosca will save those configuration values inside the XOS. And then XOS will pass these values to ONOS Fabric. Then ONOS Fabric may configure OpenFlow switch. And of course, synchronizer and ONOS controllers itself monitor ONOS controller container or Fabric. And we have a configuration UI. So if you want to change some configuration values by using a UI, then you can use it. This configuration UI will send those values to send that values to ONOS controller. That's Fabric workflow. And then when slicing workflow is similar, but only three parts are changing. First one is this Tosca file. We should use a new Tosca file. So it has new configuration, input configuration, and we will use a different ONOS controller. For different controller, we should use the different. That is the only differences. And here is some example. So here is a dashboard for us for our COMAC platform, and here is a Fabric configuration UI. So as you can see that this Fabric switch is using OFDPA3 drivers, and there is a management address and OpenFlow ID there. And in this OpenFlow switch, we are using four ports, 33, 34, 35, and 37 ports we are using in this Fabric configuration. And next one is a run slicing part. So in our COMAC, we are using two UEs. Each IMSI number is there, and each ID is IMSI1 and IMSI2. And then the last one is eNodeB configuration and run slicing. So we are using XLR and eNodeB, and IP address is over there. And we define two slices. First one is for file download, and second one is for video streaming. So for download slice, we allocated 5% resource blocks to IMSI1 UE. With, and also this slice is using a round robin scheduling algorithm. And likewise, video slice has 50% resource blocks for IMSI2 UE, and also using a round robin scheduling algorithm, we can define like this with Tosca files, or you can change this UI. Then synchronizer will pass this values to ONOS controller, and ONOS controller will change the eNodeB. Yeah, that is all from my side and our session. So, do you have any questions for all parts, or some suggestions, comments, and doubts? Yeah.
How you deploy? So in your you talk about XOS, but all you actually synchronize and actual deployment is on all nodes, right? You didn't try Cumulus, anything like that, right? Okay, thank you.
Just use XOS for ONOS controller now.
Okay, okay. And going back to CDN, right now you only have like one remote node. Do you plan to do it later on? Later you can discover distance, like which server, remote server is closer, so you can pipe it closer. Do you plan to do that?
We can discuss about that.
Are you going to use OpenStack at all for any of the infrastructure layer, like the VIM, or are you going to be only using Kubernetes?
Several years ago, our first version is based on KVM. Then the second version based on OpenStack. Then right now we moved to Kubernetes. 1 year and 2 years ago, we used OpenStack before.
What is the latest version, you said?
Kubernetes.
Okay.
Yeah.
Any other questions for our session?
15 minutes break. Then we come back around 11. We start the installation and the hands-on tutorial. Okay.